Hello everyone. Welcome to today's session. And today we look at module number 4, the physical layer. In the previous module, we discussed protocols and models, and most importantly, we looked at the OSI model. We looked at the 7 layers that makes up the OSI model, helping us break down a complex system that we call a network. That was how we put across the OSI model, a system that helps us understand complex systems, a model that helps us understand complex systems. Now, in the following chapters, in the following modules, we're going to discuss each and every level of the OSI model because I think it forms the basis of our understanding of what networking is. So we'll look at the physical layer as a separate module, the data link. We'll look at the network layer, the transport, then the application. So all the other 3 layers, they're bundled up together and we'll look at them as the application layer. So this is the first of the layers that we're going to be looking at, and it's the physical layer. So the physical layer basically is the foundation of all network communications, dealing with transmission of raw data over a physical medium. We've discussed physical media before, um, wired, wireless. We discussed copper, we discussed fiber, we discussed the coaxial cable. So that's where we have the types of media that we will look at. The physical layer forming the foundation of network communication, dealing with transmission. And some of the key responsibilities of the physical layer is defining the physical characteristics of a connection. For example, the type of cable that you are going to be using, the type of connectors that you are going to be using, the pin configurations that you're going to have. So that's one of the key responsibilities of the physical layer. What is the type of cable? What is the type of connectors that we're going to be using to make our connections? Right. It also deals with transmission of raw data, transmission and receiving of raw data is electrical signals, optical signals, radio signals. Depending on the type of media that we have, we're going to have mainly those 3 types of signals. So the physical layer deals with the transmission of that raw data. In the physical layer, we also have encoding and decoding. I think in module 3, we defined encoding as uh, changing one format into another format so that it is suitable for transmission. Changing one format of information or data into another format so that it is suitable for transmission, right? So the physical layer is also responsible for changing the format that we have coming from the application layer, encapsulating that data segment. We have the packet, we have the frame. Then the frame is changed into a format that is suitable for transmission, depending on the type of medium that we have. Kana tine optical fiber, the format is changed to light because optical fiber uses light. If we have copper, it is changed to electrical signals. If it is wireless, it is changed to an electromagnetic wave. That change is what we call encoding. So basically, that is what the physical layer deals with, and that is what we're going to be looking at today. All right, module objective is to explain how the physical layer protocol services network media. Network media support communications across data types. And we'll look at the purpose of the physical layer, its characteristics. We'll look at copper cabling, UTP cabling, fiber, and wireless media. So I think that that is the main type of media that we have. The wired, wireless, copper, fiber, and for wireless, we have the wireless media. And I think that summarizes, that makes up what we call the physical layer. Right. Purpose of the physical layer. Before any network communications can occur, a physical connection to a local network must be established. This connection could be wired, wireless, depending on the setup of the network. And this generally applies whether you are considering a corporate office or a home office. We have the NIC connecting a device to the network, some devices having one NIC, while others having multiple NICs. Not all physical connections offer the same level of performance. Okay, this is basic. The NIC, you need to understand what is the NIC. The NIC is a component of a device that allows it to connect to the internet. And I think a very good example of an NIC, we have a laptop. A laptop, some laptops, they have NICs built in. That allows you to connect that Ethernet cable to your PC, to your laptop. That Ethernet, that NIC is built in. That's a wired NIC. Laptops that we are using today, I think the tech is up there. They have also the wireless NICs where you can create a hotspot, connect to the Wi-Fi with your laptops. All of it is built in the laptop, the NICs. Then we have, I don't know if you've ever used ka, ka NIC not built in papa oil. Kanotengwa as a USB, so go to no connector. Then that allows you to connect to a Wi-Fi, to a hotspot. I'm forgetting the name of that device, but it's an NIC. The technical name, that's an NIC that you buy, which allows you to connect to the hotspot. That is not built into the computer. So basically, an NIC, I can say it's a hardware that plus software as well, a device that allows you to connect to the internet. Without that, you won't be able to connect to not the internet, to a network. You will not be able to connect to a network. Right. So to summarize, a physical connection is required for us to start communication. The physical layer transports bits across the network media. It accepts a complete frame from a data link layer and encodes it as a series of signals that are transmitted to local media. So looking at the OSI model from top down, when we get to layer number 2, the data link layer, we talked about framing, where the data that you have coming from the application layer gets encapsulated up until it gets to layer 2. We have a frame. That frame needs to be converted into a series of signals that is transmissible over media, encoding, definition. Right. This is the last step of encapsulation process. The next device in the path to the destination receives the bits, re-encapsulates the frame, then decides what to do with it. So basically, this is a summary of the process between layer number 2 and layer number 1. From layer number 2, we have framing. Then this framing is converted into bits, right? These bits is then converted into a signal, which can either be electrical, light, or radio. Electrical, copper media, fiber, wireless media. And this is what happens in the physical layer. I think this is just a repetition of the introduction that I just gave. That is the responsibilities of the physical layer. And what is being demonstrated here, basically, right here, is the encapsulation process. I think it's worth repeating what the encapsulation process is. Putting a letter into an envelope, that is what encapsulation is. Putting a message into another message. What do we mean by that? At the application layer, at the top, we have the message that we are trying to send. At the top of the layer. The message that we are trying to send There it is. That's the data in the application layer. Then as it goes down the layers, it gets to the transport layer where it is encapsulated. A header and a trailer is added. Then from there, we form what we call a TCP segment or a segment. Then that segment, another header and trailer is added at the layer 3, forming a packet. At layer 2, another header is added, forming a frame. And that is the process of encapsulation. Then the inverse of that, de-encapsulation. So if you are going from top down, where are we sending from? Right. If we are going from top down, from where the message is coming from, where we are receiving the message, it goes from top up. De-encapsulation. So all the headers, all the trailers that we were adding, we start removing them so that we get to the data. So zvangofanana nekubvisa envelope. Later ukauya ukasabvisa envelope, you won't see what is inside. So de-encapsulation is removing that envelope so you can see the information that is inside. So encapsulation, de-encapsulation, very important to understand. Characteristics of the physical layer. Starting by the physical layer standards, we defined, I think we defined standards, open standards in module number 3. And we say we have open standards. Why we have open standards is so that we have interoperability between devices from different manufacturers. I think that's the big one. And we discussed these standards being run by different organizations. Some of the organizations, there we have them. And I think I gave you a task. It's very important for you to understand what each and every one of these organizations do. ISO, for example, the basic thing, I know ISO by inventing the OSI module. Develop. ISO. That's the organization which developed the OSI module. I know EIA/TIA. That is, the organization responsible for developing standards for cabling, the type of cables that we use, which is characterized by the capacity of those cables. So the EIA/TIA organization is responsible for those standards. So kuti kana cable is transmitted at 10 megabytes per second, at 100 megabytes per second, possibly we call that cable Cat5e. That's the standard. So if you want to have a cable in a capacity 100 megabytes per second, you will need to use cable known as Cat5e. Right? That's the standard. So the EIA/TIA guys are responsible for that. Right? Standards for cabling, standards for my connectors, the type of connectors that we use in networking, and many other physical layer components that we use. Then we have ITU, which is responsible for standards in telephony, telegraphy, and data transmission. One of the big things last year that I heard about ITU, they were in Dubai, and our Minister of ICT went to Dubai. I remember that. What's her name? Minister Mawetera, I think. She went there, and the core business was deciding what are the frequencies that the world needs to be using. Communication is run on frequencies. What are the frequencies that we are going to be using in this world? There are frequencies which are not supposed to be touched because they are critical frequencies which are being used maybe for critical applications. I gave an example of frequencies that are being used by our radio. You are not allowed by law to use the frequency which is being used in Star FM or Power FM. So it's the same. Who decides that? The big organizations which is responsible for all the frequencies that we use for communication, this one, ITU. Right? We also have, I'm not familiar with this one. We also have IEEE. I will leave this one for you. I'm not so familiar with that. Right? We have IEEE, which is responsible for I think some of the important standards that we have in communications, the Wi-Fi standard, wireless LAN, the wireless LAN standard IEEE 802.11. We also have 802.3. That is Ethernet. That's the Ethernet standard. That's the Ethernet standard that we have. I know Bluetooth. I think Bluetooth is 802.15. Let me try to write that down. Bluetooth. So this is wireless LAN. This is Ethernet. You need to know these standards. Very important. Because going forward, you probably not see wireless LAN that much, but you see IEEE 802.11. Then we have 802.15. I think this one is Bluetooth. Should be. So that's a standard. Bluetooth is a standard. It's a standard developed by IEEE, right? Physical layer standards. So all these standards that we are discussing, and the governing organizations that are responsible for those standards, they belong in the physical layer. I can't see your screen. All right. Can you see my screen? Anyone who can see my screen, comment quickly. Someone is saying no screen here. All right. The screen is there. You might need to rejoin, exit the meeting, rejoin. All right. So I was saying all these standards, all these organizations, that those are the standards that we have in the physical layer. So you will see we have other standards in other layers, but for now we're focusing on the physical layer. Physical layer components. So physical layer standards address three functional areas: the physical components, encoding, and signaling. We are going to be looking at encoding and signaling in the next slides. The physical components are the hardware devices, media, and other connectors that transmit the signal that represent the bits. Hardware components like the NIC, interfaces, connectors, cable materials, and cable designs are all specified in standards associated with the physical layer. So I've already said, for example, EIA is responsible for these cable designs. How are the cable designed? What is the cable materials? What is the materials being used for those cables? There are standards for that. What are the type of connectors that are going to be used to connect our devices or to connect our networking cables? There are standards for that. And organization responsible is EIA. So physical layer standards, moving, encoding. All right, by definition, this is the process of converting data or information from one format to another format, especially when it is crucial for efficient transmission of that signal. So you can convert from one format to another, but if it does not lead to efficient transmission, then I'm not sure if we can define it in encoding as encoding, because encoding, we do encoding so that we have efficient transmission. If we don't do that, our transmission is not that efficient. Our transmission is not that secure as well. There is incompatibility as well between devices. So in terms of transmission, if you have a signal like this and you want to transmit it using fiber, this won't be transmissible using fiber because this is an electrical signal. I can see voltage is there. This is an electrical signal, all right? You won't be able to transmit that if the medium is fiber. So what do you have to do? You have to encode. You can change this format to a format which is light. So for example, if we are going to use light, I can say this is light on, this is light off. So when the signal is going, it's on, off, on, off, on, off, on, off, on, off. At the other end, you decode. What does on, off mean? On, off means 10, 10, or high voltage, low voltage, high voltage, low voltage. That basically what is encoding and decoding is. if you want to transmit a signal and if you want to be efficient, which is obviously dependent on the type of media that you are using, then you need to change between formats. Also, another thing of compatibility. This is very important. Encoding is very important for compatibility. You might have device A which understands, okay, which understands language English. Then we have device B which understands language French. For these two devices to communicate, there needs to be encoding, which converts from English to French or from French to English. So in between here, there needs to be encoding. So encoding is important for efficient transmission, number one, also for compatibility. If you have two devices which do not speak the same language, then you need an encoder in between those devices, which will act as a translator, if I can say. Then lastly, security, encryption. When you talk of encryption, that is also encoding. So security-wise, encoding is very important. If you have, I gave an example, I think last time, if you're trying to send the message silence and you have encoding here, plus encoding, the message that you'll be sending will probably like this, ECNELIS. That's an encoded message, encryption, right? So that you don't have to know. If you don't know that Ndangwesa letters are backwards, which is the key of encryption, then you won't know what the message is. I could just make those words random so that you don't know what those words are. And that is what is encryption. It is also a form of encoding. So some of all those things, they are being done in the physical layer, right? Signaling. When you talk of signaling, this is signaling method is how the bit values 1 and 0 are represented on the physical medium. So basically, signaling refers to the methods used to represent and transmit data. It can either be as electrical signals, optical signals, radio signals, which are electromagnetic waves. So signaling is basically that. What's the method that we are using to represent our signal? It can either be, okay, this is a microwave, optical fiber, electrical, or radio waves. Basically, that is what signaling is. So depending on the media, it all depends on the media or the channel. Depending on the media, we have different types of signaling. Canantine copper, the signaling that we will use is electrical signal. For fiber, we have light pulses. Then for a wireless medium, we have microwave signals, radio signals, electromagnetic waves, same terminology. Right, bandwidth. The first time I introduced bandwidth, I defined bandwidth as by giving an analog. I gave an analog of a 30-ton track and a Honda Fit. I think that's a half ton Honda Fit. I'm sure it's 600 kgs around there, but can go to a ton or a two. Right. I gave an analog of that bandwidth. If you have a 30-ton track, it has a huge capacity. Unokwanisa kutakura zvinhu zvakawanda. It's the same thing here in communication. Bandwidth is the capacity at which the medium can carry data. If the capacity is larger, wider, huge, I don't know. If the capacity is big, okay, let's use big. If the capacity is big, it means we can carry a lot of data. If the capacity is big, we can directly relate that to the speed as well. Because we have a big capacity, it means the speed at which we move our information, our data, will also be big as well. Digital bandwidth measures the amount of data that can flow from one place to another given the amount of time. How many bits can be transmitted in a second? Physical media properties, current technologies, laws of physics play a role in determining the available bandwidth, right? So depending on the type of media that we have, it defines the capacity of the medium that we're going to have. So for example, copper, if we are to compare copper and fiber, they have different mediums. Fiber, I think, having the largest bandwidth of those two. And I think of any medium, if I can say, fiber is probably the medium with the biggest bandwidth, fiber, right? Why? It's because of the laws of physics, which we cannot get into today. Uh, Basically because of the laws of physics in the type of media fiber is. Losses as well. It has very low losses, which also contributes to the bandwidth being very high. Right. Why is bandwidth important? Why is bandwidth important? It's important when we are discussing the physical layer because it defines how much data we can transmit in a channel that we have. Bandwidth is very important because it defines in the physical layer, it defines the amount of data that we can push, the amount of traffic that we can push in a medium. I also want to give another analog of bandwidth. Allow me. Bandwidth is like a highway. A highway, and the wider the highway, the more the bandwidth that we have. The wider the highway, it means we can have multiple cars ziri kufamba simultaneously in that highway. Kana iri shorter, iri smaller, it means we cannot do that. Highway kana yakakura as well, it means mota inokwanisa kufamba speed yainoda because lane riri clean, riri clear of any traffic. There is no congestion. You don't get easily congested. So it means motikari inokwanisa kufamba at faster speeds. I think that's a perfect analog of what bandwidth is. Bandwidth ikakura, it means we can carry more data. It also means speed increases because there is less congestion. The path yet traffic yedu inenge less congested, therefore leading to more speeds. Units of bandwidth that we're going to be using, bandwidth bits per second. This is 1,000, 1 million, 1 billion. This should be 1 trillion. I think so. Terabyte, gigabyte, megabyte, kilobyte. I think that those are basics that you need to know. Bandwidth terminologies, we can relate bandwidth to those three things: latency, throughput, and goodput. Latency being the amount of time, including delays, for data to travel from one given point to another. Latency is very important. If the latency is very small, it means communication here is perfect. For example, this session that we did, if the latency is big, I can say hello at 2100 hours. Iwozonzwa hello at a minute past. That is not good for communication. It's because the latency is low. When you buy, for example, your internet packages, okay, probably won't apply in Zimbabwe. We don't look at it that much. But internet inofanira kunge ine latency yainayo, and that should be very, very small. So that kana uri kustreama, for example, vamwe vanhu vacelebrate maresults ebhora ragohwa iwo usati watomboona kuti ragohwa. That is latency. The delay, that delay between what is happening at one end and what is happening at your end. If the bandwidth is big, most probably the latency is low. When we talk of throughput, this is the actual rate of successful data transmission, a measure of the transfer of bits across the medium over a given period of time. I think I'll explain this using the highway analog again. Highway medu, let's say we have 10 cars. 10 cars can at the starting point, do data ready to transmit. At the destination, probably not all 10 cars will get there. Maybe dzimwe zichasara congestion, maybe dzimwe zichaita accidents. Throughput, imotikari dzasvika at the destination dzese, that's throughput. So throughput defines the actual rate of successful data transfer. Then when we talk of good put, this is the measure of usable data transferred over a given period. Pa7 dzasvika dzakatakura zvatiri kuda chaizvo ndedzipi? Pamwe 5 chete ndo dzakatakura, dzimwe 2 dziri empty. So good put i5 motikari dzasareko. And good put is the effective throughput after considering, when we go to networking communications now, good put is the effective throughput after considering packet loss, retransmissions, and packet overhead. Because pamotikari dzese dziri kuenda tataura kuti process encapsulation, encapsulation. For process encapsulation, we are adding my headers and my trailers, right? But my headers and my trailers is not the actual information that we need, the data that we need, the message that we have transmitted. My headers and my trailers is extra weight it is per message so that we can be able to transmit it, right? When we remove my headers and my trailers, doing on the traffic overhead, that's how we get the good put, right? I think that's good enough. Terminology, copper cabling. Let's move. Characteristics of copper cabling. This is one of the physical media that we are going to discuss, including fiber, two-wired media. I think we're also going to look at coaxial cable. Copper cabling is the most common type of cabling used in networks today. It is inexpensive, easy to install, low resistance. It has a low resistance to electrical current flow. All right, copper cabling, I think communications, as we know it, the foundation, the core of communications, it was copper. We have what we call the PSTN. I don't know if there's a telecommunication guy there. We have what we call the PSTN, which is the core of all the communication that we have, I think, the PSTN. It is mainly, okay, we have someone in chat. It is mainly copper. However, it is being replaced by fiber. And the reason why, data, copper with its low bandwidth was good enough. What we needed copper for was to make my phone calls. I think doing a critical application to make my phone calls. And making my phone calls, it doesn't require that much bandwidth. But today, we stream live videos. That requires a lot of bandwidth, which copper does not have the capacity to do. That's why some of the links in PSTN app is being replaced in fiber. So copper cabling is the most used because it's cheap, it's easy to install, it's inexpensive. Does inexpensive mean cheap? Because copper is copper cheap as well. Yeah. Copper is not cheap. I'll explain later on when I look at fiber. Inexpensive, easy to install, low resistance to current flow. Its limitations, attenuation, number one. Attenuation, loss of power signal. If power signal starts at, let's say, 30 microwatts, input rozosvika 0.03 microwatts output. That is what we call attenuation, loss of power. If a signal loses its power, it means you won't be able to receive anything at your destination. So kana signal in attenuation yakawanda, all the signal gets lost over transmission, right? That defines what attenuation is. And here we see that copper in a very high attenuation, meaning the longer the electrical signals you have to travel, the weaker they get. Saka kana distance yakakura, we have weak signals being transmitted. That's why it's being replaced in a fiber. Because fiber, you cannot easily attenuate the signal of fiber. The electrical signal is susceptible to interference from two sources. Right? We have interference, two types of interference. That's a problem for copper, which is not a problem for fiber, by the way. We have EMI, electromagnetic interference, and radio frequency interference. Same thing. Electromagnetic interference, those are external disturbances, external electromagnetic disturbances that degrades the performance of an electromagnetic system, electronic system. So, for example, my fluorescent lights, they affect communication. Kana only my fluorescent lights, they definitely affect how you communicate. If urushandisa copper cabling, the signals, the waves, electromagnetic waves, the fluorescent light interacts with the signal riri kufamba mucopper yaurushandisa iwowo. And that's a problem. The signal gets distorted. Other examples, even my power lines, they also distort signal ring copper. That is what we call electromagnetic interference. Now, when we talk of radio, this is mainly because of the radio waves, radio transmitters, even my phone around area. That's a problem. Okay. Let me stop minutes. Thank you very much. Let me stop here so that we can continue discussing characteristics of copper cabling.